This is another module on the probability of weather type that involves scenarios for forecasters. This one talks about 3 different winter scenarios. The first one we're going to talk about is ice accumulation within the probability of weather type and ForecastBuilder infrastructure, and the influence of wet bulb temperature stemming from the research on the FRAM ice accumulation technique. So let's get into that. The ice accumulation in the FRAM research was somewhat interesting in the observations. The ice accumulation was actually observed in the observational database from Sanders and Bargenbroek at temperatures greater than 32 degrees Fahrenheit. But what was interesting is that the ice accumulation was rarely observed when the wet bulb temperature was above freezing. So wet bulb temperature seemed to be a nice discriminator, and especially temperatures below freezing for the wet bulb temperature are more preferable for ice accumulation. In their study, just citing some details here, of the 405 hours of accumulating ice with temperatures at or above freezing, only 15 hours of those had a wet bulb temperature at or above freezing. So most of the ice accumulation was occurring at wet bulb temperatures below 32 Fahrenheit. So what we tried to do is build that into the probability of weather type science portion and discrimination of what liquid hydrometeors falling to the surface would freeze and should go to the ice accumulation. So let's take a closer look at how then the ForecastBuilder and probability of weather type take this research into account. There's basically 3 classes when we have liquid hydrometeors coming into the boundary layer, and it's based on temperature and wet bulb temperature. So the first scenario is when our temperatures are above freezing and our wet bulb temperatures are also above freezing. In that scenario, then, we have an all rain forecast. When our temperatures are above freezing and our wet bulb temperature is at or below freezing, then we have a mix of rain and freezing rain. And we'll get more into detail on the next slide on this middle case. When our temperatures and wet bulb temperatures are both equal to or less than the freezing mark, that's pretty straightforward. We're going to freeze that and accumulate ice for 100% of the QPF that falls. So again, let's look at this middle case when temperatures are warmer than freezing and the wet bulb temperature is equal to or less than 32. So here's I'm going to just talk about the curves that we put in place for the probabilities of freezing rain and rain. So this is for cases where the wet bulb temperature is at or below freezing and the temperature is at freezing or above. Above freezing here in this scenario. So at 32 degrees, our probability of freezing rain with a wet bulb temperature of freezing or less is 100%. Our rain probability is 0. As we warm temperature but keep our wet bulb temperature at 32 or less, and our temperature is now 33, our probability of freezing rain starts to diminish rapidly. We have a 26% probability of freezing rain with a 100% probability of rain. And then by 34 degrees, the probability of freezing rain is quite low at 10%. So really, we're just going to be accumulating ice at 33 degrees for a temperature, and when our wet bulb temperature is at or below 32 Fahrenheit. So let's just look at a scenario in the grids of how this would work from a gridded standpoint in the probability of weather type. In this scenario, we're going to start with a boundary layer temperature here measured at roughly 32 degrees in our forecast grid for the afternoon. So the 32 degree line is seen in red. To the south of that we have 33 degrees, and a little bit further south we have 34. So let's now look at the dew point, which we just took the temperature grid, we populated it into dew point and then dropped it by 1 degree. So our dew points here now south of that line are 32 degrees and then 33 degrees, right? So according to the FRAM, when our wet bulb temperatures anywhere around 33 degrees or above, we do not accumulate ice. And so in this case, here's my dew point of 33. So in this case, this is going to be my discriminating no ice line, provided that I have liquid hydrometeors coming into the boundary layer here. So dew point 32, and again, temperature 33 in this regime just south of the red line. So the temperatures aloft in this scenario, this is the max wet bulb temperature aloft. And although this is covered more in depth in the isothermal warm layer scenario training module, I will say that one note here is that when your surface temperature is above 32 degrees, we no longer use the max wet bulb temperature aloft curves, and instead we use this. We look at the max wet bulb aloft and do slightly different scenarios. So in this scenario here, we have basically an all liquid scenario assumed once we're at 1 degree Celsius. So basically in this scenario, when the surface temperature is above 32 Fahrenheit and the max wet bulb temperature aloft is 1, we assume a liquid outcome and an isothermal layer just above 0 for some depth to bring us to that liquid solution. So in this scenario then, with that max wet bulb temperature aloft, we have our freezing line again, and then you see our probability of rain. And recall from the table that anywhere the temperature is greater than 32, where it's 33 or 34, like in this area here, that rain is 100% conditional probability. And then here is our freezing rain. And what I did was put the table up on top here just as a reminder that when our wet bulb temperature is less than or greater than 32, which is over this entire regime, that we have the possibility of freezing rain probabilities come in greater than 0 at temperatures of 33, and then it drops down to a temperature or a probability of 10 at temperature of 34. So simply by using this chart and looking at the profile here for the probability of freezing rain, you can assume what the temperatures are. We know that the wet bulb temperature is at or less than 32 for this entire area. But I'm going to give you a minute and you can stop the video. I want you to tell me what the temperature regime is in these two areas of the 26 and of the 10% in here. Okay, so in these two areas, the temperature is 33 Fahrenheit, where it's 26. That matches this line here on the chart. Probability of rain is 100%. Remember, I can go back and show you that. Probability of rain everywhere here. Probability of rain 33 and 34 is 100% because we're above freezing. And then the probability of freezing rain is 26. And then where it's 34 degrees, it's 10%. So we have this dropping, this probabilities dropping off rather rapidly once our temperatures continue to warm. So when we look at the ice here, again, this is a slightly different map, but we're going to look at our ice accumulation in this 26% area. Again, nothing for the 10% area. This is everywhere that you see a freezing rain probability of 26%. You see some of that QPF converted to ice accumulation. And the ice accumulation on the northwest side of this band is a little bit less because there is also some probability of snow that has made its way into the forecast where the temperature gets a little bit colder on the northwest side. So it takes a little bit away from the ice accumulation there. So the next module here that we're going to go into, or next training topic that we're going to go into, is the use of road surface temperatures. In the probability of weather type, the road temp grid is used to counter the atmospheric conditions. So a couple examples here. When your temperature and wet bulb are 32 degrees or less, basically that the air is cold, but your roads are warmer than freezing, the road temp grid helps you account for that scenario. And then just the opposite, when your temperature and wet bulb are 32 degrees or warmer, or in other words, your air is warm, but your roads are cold, and you might get some freezing rain precipitation because your road temperatures are cold. The outcome for both of these scenarios is a rain and freezing rain mix. and a 50-50 split on your QPF. So it will equally be split. 50% of the QPF will go towards rain and 50% of the QPF will go into freezing rain, which will make the lighter ice, a lighter icing amount for both of these scenarios. So let's just take you through a scenario here. The temperatures are all 32 degrees. The dew points are less than 32 or 32. It's basically the scenario we just left off with in the FRAM example. So we're just going to again look at the afternoon period. And the road temp grid is found under the top-down grids. And so the forecast builder will take us to that view for the browser group. And you notice that there is no road temperature grid at this time, nor do we have an option to initialize with anything. This is a hand-drawn, edited grid that you will need to add in the probability of weather type. So in this scenario, notice that before we hand edit any temperatures or road temperatures, notice that our probability of freezing rain is still 100% like our last scenario, and our accumulation of ice is 5 to 6/100ths of an inch. So let's restart the forecast builder, seeing that we have a freezing rain scenario on our hands and temperatures are 32 degrees. We're going to go into the forecast builder and show how to use that road temp grid. We're going to use it on the afternoon again, and we're going to go to the top-down grids. And what we're going to do is we're going to work this from a freezing rain scenario into a freezing rain and rain mix based on the road temperatures that we see. Now, IRIS is a really nice source of road temperatures. You can plot the DOT information from the road sensors and get a feel for what your road temperatures are actually doing out across your forecast area. So what we're going to do here is just make a grid. And really the only important thing to do here is if your temperatures are below freezing and your roads are warm, just make a road temperature grid with some values that are some value that's warmer than freezing. It doesn't matter what it is. So we can populate this with anything, 35, 40 degrees, 45 degrees, it just doesn't matter as long as it's above freezing. So what we're going to do is we see an area where the temperatures on the roads look like they could be above freezing across our southern forecast area. So in this scenario, what you could do is you could take your road temperature grid and populate it from the temperature, and then just draw an edit area to increase the temperatures within that area to something above freezing if you wanted to do it that way. It's up to you how you want to do that, as long as it's above freezing. But in this scenario, we're going to just show what would happen here with a scenario where you allow your temperatures to fall a little bit during the afternoon hours, but they still remain above freezing across the southern portion of the forecast area. And we'll just interpolate that, clear our edit area, and then you can see our temperatures for the roads across the southern portion of the forecast area, mainly Wisconsin and northeast Iowa, are still remaining above freezing in this area. So this is a scenario where the wet bulb temperature and the temperature both suggest we should have icing, but you've gotten road information that suggests the roads are still warm. And so we're trying to account for that. And so we're going to go to the precipitation type creation, and remember, previous to rerunning these, which we'll see here, we just had a freezing rain grid there in the afternoon, the pot freezing rain. But let's remake it and notice now that you have a pot rain and a pot freezing rain grid. And that pot rain grid is 100% over the southern portion, that edit area that you drew, or the southern portion of the forecast area. And then freezing rain is also there. So our mix is in the south, and that's where we'll see our ice accumulations drop off. And that's because we're doing a 50-50 split on the QPF. So you notice 3/100ths of an inch over southwest Wisconsin and northeast Iowa, and 6/100ths of an inch over the farther northern areas. And the line ice accumulation is even less than that. And then just to give you a feel for what the weather grids look like during that scenario, you see down in the southern portion of the forecast area a rain and freezing rain mix, where further northwest, freezing rain is the only outcome there. So let's go through the banded snow accumulation with temperatures in the 30s. And this is more of an example of how to handle a forecast the correct way rather than change the probability of weather type and ForecastBuilder user interface temperature settings. So recall that in the step where you create precipitation types and accumulation grids, that the ForecastBuilder allows you to use 34 or change these values for the threshold for all snow of 34 and the threshold for all liquid at 37. Now, there are very rare occasions where this would actually be changed by the forecaster. One scenario may be where your temperature is 36 and your wet bulb temperature is 28 or 27 and quite low, and so you are actually seeing snow falling at temperatures of 36 because your wet bulb is so low. That might be one scenario where you change this. It is important that when you do change these values that you collaborate that outward to your other neighboring forecast offices so everyone can keep the same precipitation type and snow accumulation and possibly ice accumulation as well. One of the scenarios that you might be tempted to change those numbers for is a snow band. You might be frustrated that you expect a snow band to form and that you just can't get accumulation of snow in your temperature grids that are at 35 or 36. And so your temptation might be to lift the all snow threshold to 36, even though your wet bulb temperatures might be 34 degrees or 33 degrees Fahrenheit. So what's better to do is actually build the snow band environment for the snow band into your temperature grids to reflect the heavier snow and the diabatic cooling that'll likely occur in the surface temperature. As that heavy snow comes down, temperatures are likely to cool down to 32 or 33 degrees Fahrenheit. One of the nice tools that is recommended to look at are the high resolution models in the wintertime. So some of the convective allowing models and the higher resolution core models. You can see that this case scenario here is the high res window ARW core. And in this scenario, it's May. Notice it's May 2nd here. And the model is developing a snow band across southeast Minnesota, far north central Iowa, southeast Minnesota, and into northwest Wisconsin. Notice the temperatures on each side of that snow band in the 37-degree range in the morning hours and up into the 40s. So this band is a snow band in the model. You can see the reflectivity in the lower right and the precipitation type and intensity here across southeast Minnesota. And what's happening there is that just diabatic cooling in the model is giving you some clue that you're going to drop your temperatures down within that snow band. So typically you'll see this occur at longer time scale forecasts, longer forecast lengths as well. And so it's something to really try to hone in on and use as guidance in your forecast grid. So let's just do that. Let's draw that temperature grid in, and let's draw in and add a snow band over southeast Minnesota. Notice here the dew points are all below freezing, so what we're going to do is just lower the temperatures. Our QPF is around 1/10 of an inch. This is the scenario we've been using for the first two examples for the FRAM and the road temperatures. So what we're going to do is just do a quick check on the max T aloft. The one change we've made is we've cooled this all off now, so it's an all snow or all rain forecast. With temperatures aloft being cold and only boundary layer warmth changing it from a rain or snow forecast. So just reviewing the probability of weather types here quickly, the snow is off to the northwest where we have temperatures that are quite cool, and the rain is everywhere to the south, and in the middle, that 34 to 37 band is where we see the rain and snow mix over southeast Minnesota into north central Wisconsin. So we're going to start up the forecast builder. We're going to run it during the afternoon. We'll just pick today, and we're going to start with the foundation and base grids. And we're going to start by editing our temperature down into that below 34 regime so that we can start accumulating snow. We're not going to initialize any grids right now. But what we'll do is hand edit the temperature field to reflect colder temperatures within a snow band. Okay, so now we've edited those temperatures just using the pencil tool to drop them in the snow band, drop them below 34 degrees, where we think that band's going to present itself, similar to the example we saw for May 2nd, 2013 in that high resolution WRF window forecast. Let's just save those temperatures there. And then just to be consistent, let's increase our QPF over that area as well. Obviously, in a real-time scenario, you might have more data sets for QPF that are available, and you might consider just initializing with the cons short data that would have been in that previous step where you could click on QPF to see what it looked like. Here we're just going to value it up and just do a hand edit on it for this scenario as an example. There we go. So I've bounced that max up to about 1/4 inch of liquid in that snow band area, and I'm just going to smooth it out a little bit, hit it with a couple smoother runs there. And so my QPF has been edited for that snow band, and we've cooled the temperatures in that due to diabatic cooling with the snow rate. Just as a quick look, our snow ratios are about 12 to 1 in this scenario. So we're going to continue on. This again was the foundational step of the forecast builder. Now we're going to go to the top down grids, and we're not going to do anything here. No reason to change those grids. Everything's below 0 aloft. Finally, to come into our step 4 of the forecast builder, where we're going to create the precipitation types. Again, remember there's a rain-snow mix. And we're going to keep those settings at 34 and 37 on the GUI window. Again, rain-snow mix was currently over southeast Minnesota and north central Wisconsin. We're going to remake those grids and our accumulations. And so our rain forecast now you can see is 32, where the 34 degree temperature line is now across southeast Minnesota. We've converted that over to all snow in southeast Minnesota. You can see that there's no rain probability there. And likewise, our snow amount grid has created our snow band in that area. So that just provides a nice example of how to build in that snow band and not worry so much about the temperature GUI and changing your temperatures. You know, the science, build in the science and the probability of weather type grids or into your grids, and the science within the probability of weather type will give you the outcome that the science will drive.